In this video, we're going to solve the Schrodinger equation for the harmonic oscillator, and we're going to use the factorization method. So let's start out by writing out our potential, which is 1/2 times the mass times omega squared times x squared. And let's just take a look at these units really quick. So we have this omega term here is going to represent the frequency of oscillation. So omega has units of 1/seconds. X is the position operator. It'll have units of meters. Right? And then our mass will have units of mass, of course. So omega squared x squared will have units of velocity squared. And then if we have units of mass times velocity squared, we just have units of energy. So that's how you make sense of this potential. So let's go ahead and start solving our equation. And the equation we want to solve is the time-independent Schrodinger equation, which looks like this. So firstly, let's write out our Hamiltonian. We have our kinetic term, which is the momentum operator squared over 2 times the mass, plus our potential. So to begin, let's rewrite our Hamiltonian in a way that's a little easier to work with. Because we want to factor this out into 2 separate operators. So if we write it out like this, it becomes somewhat easier. So let's give these operators names. Well, the first one we'll call it the raising operator. And the second will be the lowering. And the names for these will become clear in a bit once we actually get to our solution. So let's just factor this out as we would any other expression and see if we can recover this exact Hamiltonian with two operators. So our raising operator is going to look something like 1 over the square root of 2m times negative I, which is the square root of -1, times the momentum operator plus mass times omega times x. And then if we choose our raising operator to look like this, then what we have to do is make our lowering operator essentially the same thing, but with the sign here flipped. And this is so when we multiply them out, we hopefully get terms that cancel. And let's see what happens. And if you're not familiar with working with operators, the order in which you multiply them out actually makes a difference. So this is not going to be equal to this generally. So we have 2 things we want to compute. Let's start with the first one. Okay, so then if we then get these cross terms, we have I times mass times omega with momentum coming before the position, and then the position before the momentum here. And again, we have commutators here, so it looks like these terms should cancel each other, but they don't because the momentum times x is not equal to x times the momentum. And let's write this in a way that's a little more clear. So this is the term that we want to compute now, and this is something called a commutator. In this case, it's the commutator of the position and the momentum operators, and this is equal to what we have written over here. And it's sort of a measure of how much these terms don't commute with each other. So if you want to flip them, you're going to get some extra term, and this is the extra term that you're going to get. So the way we go about actually figuring out what these commutators are is we throw in a test function and see how it acts on the test function. So, and then recall that the momentum operator is negative I h bar times the first derivative with respect to x. So if we pull out the negative I h bar, we have and then we can just use the product rule over here. So these two will cancel each other, and we have I h bar times our test function, which we can now get rid of. And this is the commutation between the position and the momentum. And this is the most important commutation relation in probably all of quantum mechanics. It'll pop up everywhere. So let's put that in now to our expression for the raising times the lowering operator. So when this I hits this one, we're going to get -1. And then I'm just going to pull this out of the parentheses here. I'll pull that extra term out so that we can separate what was our initial Hamiltonian from the rest. And we have negative h bar omega over 2. And this is the raising times the lowering. So if we were to have done the lowering times the raising operator, we would have gotten a similar thing. But the only thing that would have changed is our extra term, when the sign would have been flipped. And the reason for that is because the only thing that would change is the sign of or the order of this commutator, which is just multiplying it by -1. So we have plus h bar omega over 2 as opposed to minus h bar omega over 2. So now we can rewrite these terms in terms of our Hamiltonian. And then we can rewrite our Hamiltonian in two separate ways. And this will all be useful to us in just a bit. So where should we go from here? Because we were intending to reproduce our initial Hamiltonian, but we're left with these extra terms here. And it turns out that these will be useful to us because they're going to determine our energy levels. And the way that works is as follows. So there's a nice theorem that we're going to prove right now, which is that if we have some solution to the harmonic oscillator that and this is a solution, so it's going to satisfy the Schrodinger equation for some energy, then applying our raising operator onto the state is going to give us another solution with some more energy, and I'll call it E sub n plus 1 because it just represents a little more energy, and it will end up being our next energy level. So let's go ahead and actually prove this. So this is the assumption we're making. We're assuming that we've already found some eigenstate to the harmonic oscillator. So we're taking this part as an assumption. And then we want to compute this and show that it equals something like this. So now the way that we rewrote our Hamiltonian up here is going to be useful to us. We're going to substitute in our Hamiltonian for this term, or substitute this term for our Hamiltonian rather. Right? And then we're going to do another substitution. Namely, we're going to do it on this portion, And we know that this portion up here is equal to the Hamiltonian plus h bar omega over 2. So we have and this is equal to these two h bar omega over 2 terms are just going to combine. And we already made the assumption that this is already a solution to the Hamiltonian with some energy E sub n. So let's write that out. And since this is just a constant, we can move it to the left. So we're left with this initial energy plus h bar omega on this state. And this was equal to the Hamiltonian acting on our raised state. So nice. So we've assumed that this was a solution, and we showed that using our raising operator, we obtain another solution with some more energy, and to be exact, h bar omega more energy. So that's very good. These are going to be our energy levels. And if we were to have instead used our lowering operator on the state, you can guess that we would have gotten an energy minus h bar omega. And you can calculate that for yourself. It's not so hard to do. You essentially just use the same tricks we used up here, substituting the operators for the Hamiltonian and then vice versa. So now the way we proceed from here is we just claim that there's a ground state energy, and the ground state is defined as the lowest energy state, so we should not be able to go lower than it. But if we have some operator that's moving us to lower energy states, namely the lowering operator, then if we act on the ground state with this lowering operator, we should get back 0. That's the whole point. So this turns out to be a relatively easy differential equation to solve if we just substitute in its value for the lowering. And that looks like this. And then if we substitute our value for, well, we can get rid of this term. This is equal to 0. And then we just substitute the value for the momentum. And we're going to get h bar, first derivative with respect to x on the ground state is equal to, and I'm going to put this on the other side, negative mass omega times x times the ground state. And then now I'm just going to shuffle some of these terms around, like h bar and dx. I'm going to move dx to the right side, and then I'll bring this ground state to the left side, and we'll have this expression here. That's going to be easy for us to integrate. So if we just integrate both sides, we know on the left side we'll get the natural log of the ground state, and this will be equal to negative mass times omega position operator squared over 2 h bar plus some constant. And the constant that we would have gotten from the left side, we'll just absorb it into the right side and all into this c here. And now we can just exponentiate both sides, because when our exponential hits this natural log, we can just bring down this term here. So we have the ground state is equal to e to the power of c, which is just another constant. And then the exponential of mass, or the negative mass times omega x squared over 2 h bar. And I'll just rewrite this. I'll just rewrite this e to the power of c as a, because it's going to just represent our normalization constant. And this is what our ground state is going to look like. So now what's left is we have to normalize this ground state. So We know that the inner product of the ground state with itself should be equal to 1, because this is equal to the probability density of our state integrated over all of x. And anytime you take a sum of the probability density like that over your entire space, you should get back 1. Let's do that. We have 1 is equal to our normalization squared times this integral. Oh, this is, yeah, times our exponential here. Oh, but we're going to have 2 of these, so I can just get rid of this because we're squaring that. Yep. And this is a Gaussian integral, which we can just look up, and it's going to be the square root of pi h bar over mass times omega. So if we just solve for a now, we'll have mass times omega over pi h bar to the 4th root. Okay, so now we can just plug this back into our ground state, and we've obtained our ground state wave function fully. And it looks like this. So that's very good. And remember, we also, not only did we just get our ground state, we actually got every state in the energy spectrum, because we know that applying our raising operator is going to give us our excited states without their normalization factors. So this is going to be our first excited state, and then we just have to account for some normalization that's going to go along with it. So this is the first half of our work is done. We found the ground state, and we have machinery to get to the next levels. Now what's left is to determine our energy levels that correspond to each of these states. And we know that the energy levels are going to be separated by h bar omega. So all we have to do, since we know the separation, is just determine the ground state energy. So what's the minimum energy? And that's simple. That's just whatever our Hamiltonian is going to give us when it acts on our ground state. And we can simplify our calculation by rewriting our Hamiltonian. So remember, we rewrote our Hamiltonian up there as the raising times the lowering plus h bar omega over 2. And let me just double check that. Yeah, the raising times lowering times, or plus h bar omega over 2. So if we just make this substitution, and this will be helpful because when we know that when the lowering hits the ground state, it's going to give us back 0. So the Hamiltonian acting on the ground state is going to be, oops, plus h bar omega over 2 times the ground state. And then this is just going to go to 0 because this part is 0. So we have our Hamiltonian on the ground state is equal to h bar omega over 2 times the ground state, which simply means that the minimum energy is h bar omega over 2. And we know that the energy gaps are h bar omega. So if we want to go to the nth excited state, which is just E sub n, we have h bar omega over 2 plus n h bar omega. And now just to rewrite this, we can pull out the h bar omega. We have h bar omega times n plus 1/2. So these are our energy levels. And our ground state energy is equal to mass times omega over pi h bar to the 1/4, and then this exponential here. And we know that applying our raising operator a certain number of times to our ground state. It's going to give us some normalization. Hold on. It's going to give us our nth excited wave function. And we're going to need to account for some normalization on the left side here. So this is the solution to the harmonic oscillator. And you can do a little bit more work to figure out what these normalizations are actually going to be, so that you don't have to recalculate them every time, but this is essentially the solution. So I hope this was helpful. In the following video, we'll solve this analytically, and we'll see just how much time and effort was saved by using the factorization method. So thank you.